Today's topic is that of exponential smoothing. So, what is it? It's another type of weighted moving average for forecasting within that area. It involves very little record keeping of past data and is fairly easy to use. The basic exponential smoothing formula can be shown as such. We have what's called the new forecast, and that is equal to the last period's forecast. And we add that to what's called alpha. And all alpha is the last period's actual demand. Last period's actual demand. And we subtract the last period's forecast. All right. So here, that alpha, it's a weight of some sorts, or we can call it the smoothing constant. This smoothing constant, alpha, is actually chosen by the forecaster. Um, and it has a value greater than or equal to 0 and less than or equal to 1, right? Greater than or equal to 0 or less than or equal to 1. So equation 1 that I just wrote out in words, we can write this more so mathematically as such. So we'll go with these variables. F sub t equals f sub t minus 1 plus alpha times the quantity of a sub t minus 1 minus f sub t minus 1. All right, let's discuss what these mean. All right, so first, that f sub t is, you guessed it, the new forecast. Right, we're just rewriting the above equation 1 more mathematically. Then we have f sub t minus 1. This is the previous period's forecast. All right, and then we said, of course, alpha is the smoothing constant, or you might hear it described as the weighting constant. And I think we just said that alpha is going to be between 0 and 1. And then lastly, a sub t minus 1 is equal to that previous period's actual demand. Right, that actual demand. So the concept of exponential smoothing is really not too complex if we take a close look at it and break it down. The latest estimate of demand is equal to the old forecast, and it's adjusted by a fraction of the difference between the last period's actual demand and the last period's forecast. So let's go ahead and take a look at this example once you've copied down the formula. All right, let's take a look. All right, here's our example. It says that in January, a car dealer predicted February demand for 142 Ford Mustangs. Actual February demand was 153 autos, using a smoothing constant chosen by management of alpha being equal to 0.20. The dealer wants to forecast March demand using the exponential smoothing model. All right, so the exponential smoothing model in equations 1 and 2 can be applied for our solution. All right, so substituting the data. So first I'll actually write that equation over again, right? We had f sub t is equal to f sub t minus 1 plus alpha times the quantity of a sub t minus 1 minus f sub t minus 1. All right, I like to always have my formula right in front of me so that I can look at and then substitute in. All right, so the new forecast. The new forecast, and what did we say was for what month? March. For March demand. And it's okay to write these things out so that you can better understand them in plain English. So it's equal to the f sub t minus 1. We said f sub t minus 1 was the previous period's forecast, and that's 142. And then we add alpha, and we're going to add that, but multiply alpha times that entire quantity that we see in parentheses. Alpha was chosen by management as 0.20, so zero point 0.2. And now we have the alpha being multiplied times the quantity of a sub t minus 1. A sub t minus 1 was the previous period's actual demand, which was 153 autos, right? And then we subtract f sub t minus 1. Well, we said initially f sub t minus 1 in the beginning of the formula was the previous period's forecast, which was 142. All right. So we just go ahead and compute. You can crunch these numbers using a calculator if you have one handy. 142 plus 2 and 2/10 gets us 144 and 2/10. So thus we can say that the March, and we like to write these things out, March demand forecast for the Ford Mustangs is, and we round it to 144. 144. So we developed a forecast of 144 Ford Mustangs for the month of March. All right, so a bit more discussion about our smoothing constant. Our smoothing constant, alpha. So this is generally in the range from 0.05 to about 0.5 for most business applications. All right. It can be changed to give more weight to recent data. When our alpha is high, or more weight to past data when our alpha is low. When the alpha reaches like an extreme value of 1.0, then let's see what happens. So if we were to go back and take the equation f sub t equals f sub t minus 1 plus alpha times the quantity of a sub t minus 1 minus f sub t minus 1, right? This is our initial formula. Now, if alpha reaches an extreme of 1.0, then let's see what occurs. I think here we can go ahead and distribute before I go ahead and substitute. So f sub t equals f sub t minus 1 plus alpha times a sub t minus 1 minus alpha times f t minus 1. All right, so alpha is going to be 1.0, we said, right? When it reaches an extreme value of 1.0. So when we have alpha as 1.0, this is going to be negative f sub t minus 1. And over here we have positive f sub t minus 1. So they'll make 0, right? And then we'll be left with f sub t is equal to alpha, which is 1.0, a sub t minus 1. So all the older values drop out, right? All the older values drop out. And then the forecast becomes very identical to the naive model. So the naive model is a model that would have been mentioned as one of the time series forecasting models. It would have been mentioned likely with maybe a moving average model or a weighted moving average model. So this now becomes very identical to that. So the forecast for the next period we see is just the same as this period's demand if alpha became an extreme value such as 1.0. All right, so this was a brief quick tutorial on exponential smoothing. If this helped you any, please hit the like button. Feel free to share with those who may need, and don't forget to subscribe. Take care all.